Chapter 1 Gravitation. In this chapter, we are going to learn about the different concepts related to gravity and gravitation happening in our daily lives. As we have studied in our previous standards that gravitation is the pull of the earth, but here we will try to understand how it was discovered. As we know, Sir Isaac Newton discovered gravitation force by seeing an apple fall from a tree on the ground. He then started the thinking process as to how and why all things fall vertically or straight downwards and not in sideways or horizontally or even diagonally. After much thinking, he concluded that there is a certain amount of force which is attracting all the objects towards itself, and this force is directed towards the center of the earth. And as the direction of an apple on the tree is vertical to the ground, so the apple falls vertically downward. It is hard to believe, but everything in the world is in motion. The basic idea Newton taught us is that motion is caused by forces. For example, you kick a ball, the force, and it flies into the air, the motion. A force is a pushing or pulling action that can make things move, change direction, or change shape. We've now already seen that forces make things move. But how exactly are forces and motion linked together? Isaac Newton's work helps us tie forces and motion together in an easy-to-understand way. Let's recollect the Newton's laws of motion. First law. Newton's first law of motion states that every object maintains its state of rest or of uniform motion unless acted upon by an external unbalanced force. For example, in the picture, the car will remain at rest when we are using it, but it starts to move when it is given a force. Second law. Newton's second law of motion states that the rate of change of momentum is directly proportional to the applied force and takes place in the direction of the force. The acceleration is produced when an unbalanced force acts on an object or mass. For example, if you use the same force to push a big stone and push a car, the stone will have more acceleration than the car because the stone has less mass. Third law. Newton's third law of motion states that for every action there is an equal and opposite reaction that acts with the same momentum and the opposite velocity. In the example of a man kicking the door will tend to move backwards. Here, kicking the door is action, and man going backwards is the reaction. Number 1. As seen in this picture, as long as we are holding the string, we are pulling the stone towards us, that is, towards the center of the circle by applying force towards it. Number 2. The moment we stop the force, that is by releasing the string, the stone flies off along a straight line, that is, tangent to the circle at the position of the stone. As per the first example, the force is directed towards the center, so it is called centripetal force. Centripetal force is directed towards the center. This force makes an object to move in circular motion. The second example is centrifugal force, as it is directed away from the center. Here are some common examples of centripetal force in our day-to-day lives. First, a merry-go-round. Second, Earth orbiting the Sun. Third, car going round a bend. Fourth, electron revolving around the orbit. The contribution of Johannes Kepler and the Kepler's laws of planetary motion helped Newton in the formulation of theory of universal gravity. According to the universal law of gravitation theory, Every object in the universe attracts every other object with a definite force, which is directly proportional to the product of the masses of the two objects and is inversely proportional to the square of the distance between them. Consider two objects, m1 and m2, kept at a distance r from each other. So, as per gravitational force of attraction between these two objects, F is directly proportional to m1 into m2 upon r square. Equation 1. F is equal to g into m1 into m2 upon r square. Let's learn in detail about the constant g. G in equation 1 is universal gravitational constant. Number 1. How to define g? The value of g is the gravitational attraction force acting between the two unit masses kept at a unit distance from each other. Number 2. The SI unit of g from universal gravitation constant g is equal to Newton m raised to 2 kg raised to minus 2. Number 3. The value of g. Universal gravitational constant g is equal to 6.673 into 10 raised to minus 11 Newton m raised to 2 kg raised to minus 2. Significance of the law. Number 1. If the mass, either m1 or m2, of one object is doubled, then force F between the two objects is also doubled as they are directly proportional to each other by equation 1. Number 2. If the distance r is doubled, then force F decreases by a factor of 4 as they are inversely proportional to each other. Number 3. For spherical objects, the direction of the force is always along the line joining the centers of the two objects, and the distance between the centers is taken to be r. Note, center is the point where entire mass of the object is concentrated, that is, at the geometrical center. Number 4. For non-spherical or irregular shape objects, the direction of the force is always along the line joining their centers of the mass of the two objects, and the distance between the two centers of mass is taken to be r. Note, center of mass is at the point of its centroid. Consider a planet revolving around the sun in a uniform circular motion. Then, the centripetal force acting on the planet towards the sun is given by equation 1. Centripetal force F is equal to m into v square upon r, where m is equal to mass of the planet, v is equal to the speed of the planet is expressed in terms of the period of revolution t. R is equal to the distance of the planet from the sun. Therefore, speed is equal to distance travelled by time taken. Equation 2, where distance travelled is equal to perimeter of the orbit is equal to 2 pi r. Time taken is equal to period of revolution is equal to t. Therefore, equation 1 becomes v is equal to distance travelled upon time taken. V is equal to 2 pi r upon t. Substituting the value of v in equation 1, we get F is equal to m into v square upon r. F is equal to m in bracket 2 pi r upon t, bracket complete, the whole square upon r. F is equal to 4m pi square r upon t square. Multiplying and dividing by r square, we get F is equal to 4m pi square upon r square into r cube upon t square. But according to Kepler's third law, t square upon r cube is equal to k. Substituting the same in the above formula, we get F is equal to 4m pi square upon r square into k. Constant 4m pi square upon k is equal to constant. Therefore, F is equal to k upon r square. Hence, equation 3, F is directly proportional to 1 upon. As we can see in the picture, when you throw any object up in the air, the object, after reaching a certain height, falls vertically down on the ground. Example, when we throw a ball upwards, it gains kinetic energy due to its motion, that is, velocity of the ball, and on reaching a certain height, it starts to fall downwards on the ground as it gains potential energy. The reason is the gravitational force of the earth, which attracts every object towards itself, that is, towards the earth's center. This means that gravitational force is directed towards the center of the earth, which makes an object to fall vertically down on the ground. If we concentrate on the Newton's law of gravitation, it states that every object attracts every other object with force. This means that in the above example, not only the earth is attracting the ball towards itself, but the ball is also attracting the earth towards itself with the same force. But the earth doesn't move towards the ball, but the ball falls on the earth. The reason behind this is the mass and less or negligible amount of velocity of the object. For example, the ball. Same reason is applicable for the moon and other artificial satellites that orbit the earth, but they don't fall on the earth just because of the amount of velocity that they have along their orbits. To find the value of g on the surface of the earth, we can calculate the value of g by using Newton's universal law of gravitation for an object of mass m situated at a distance r from the center of the earth. The law of gravitation gives equation 2, F is equal to g into m upon r square. Equation 3, F is equal to m into g from Newton's second law of motion. Therefore, from equation 2 and 3, m into g is equal to g into m upon r square. G is equal to g into m upon r square. G is equal to g into m upon r square. Equation 4, where r is equal to radius of the earth. When object is situated on the surface of the earth, since g is equal to 6.67 into 10 raised to minus 11 Newton m raised to 2 kg raised to minus 2, where mass of the earth m is equal to 6 into 10 raised to 24. R is equal to 6.4 into 10 raised to 6 m. So, equation 4 becomes g is equal to 6.67 into 10 raised to minus 11 into 6 into 10 raised to 24 upon, in bracket, 6.4 into 10 raised to 6, bracket complete, the whole square. G is equal to 9.7 meter per second square. This acceleration depends only on the mass m and radius r of the earth, and so the acceleration due to gravity at a given point on the earth is the same for all objects. It does not depend on the properties of the object. Point A. Change along the surface of the earth. the value of g is not the same everywhere on the surface of the Earth. The reason is that the shape of the Earth is not exactly spherical, and so the distance of a point on the surface of the Earth from its center differs somewhat from place to place. Due to its rotation, the Earth bulges at the equator and is flatter at the poles. Its radius is largest at the equator and smallest at the poles. The value of g is thus highest, that is 9.832 meter per second square at the poles, and decreases slowly with decreasing latitude. It is lowest, that is 9.78 meter per second square at the equator. Point B. Change with height. As we go above the Earth's surface, the value of r in equation 4 increases and the value of g decreases. However, the decrease is rather small for heights which are small in comparison to Earth's radius. Point C. Change with depth. The value of g also changes if we go inside the Earth. The value of r in equation 4 decreases, and one would think that the value of g should increase as per the formula. However, the part of the Earth which contributes towards the gravitational force felt by the object also decreases. This means that the value of m to be used in equation 4 also decreases. As a combined result of change in r and m, the value of g decreases as we go deep inside the Earth. Point D. The value of g at the center of the Earth is 0. Let's understand the concept of mass and weight in detail. Number 1. Mass. Mass is the actual amount of matter present in the object. It is measured in kilograms or grams. For example, mass of the girl shown here is 56 kilograms. Number 2. Weight. Weight is the force with which the Earth attracts the object. It is measured in Newton or Dyne. For example, weight of the girl on the Earth is 560 Newton and on Moon is 90 Newton. So to find a weight from mass, we multiply mass of an object and the acceleration due to gravity value, that is, W is equal to F is equal to m into g. The value of mass remains the same everywhere. Its value does not change even when we go to another planet. According to Newton's first law of motion, mass is the measure of the inertia of an object, whereas weight of an object changes from place to place, as the value of g is changing from place to place. As seen in the picture, weight is changing as we change the planet or satellite, but the mass remains the same. That means our weight is different on the Earth, Moon, etc. due to the effect of gravity. So when you say that your weight is 63.5 kg, it is actually your mass which is 63.5 kg. So the weight would be 63.5 into 9.8 is equal to 622.3, approximately 623 Newton. Gravitational waves. Till now, you've come across many different types of waves. For example, water waves, electromagnetic waves. All our knowledge about the universe has been obtained through these waves. But gravitational waves are different types of waves. Gravitational waves are ripples in the fabric of space-time caused by some of the most violent and energetic processes in the universe. Albert Einstein predicted the existence of gravitational waves in 1916 in his journal Theory of Relativity. These waves are very weak and it is difficult to detect them. So, a special kind of instrument was constructed by scientists for detecting gravitational waves emitted by astronomical sources. The instrument used is called Laser Interferometric Gravitational Wave Observatory. We know that the force of gravity due to the Earth acts on each and every object. Then what is free fall? Whenever an object moves under the influence of the force of gravity alone, it is said to be falling freely. For example, Number 1. When a skydiver jumps from a height, the only force acting on him is the gravitational force, and he falls down under its influence. So the skydiver is in free fall. Here we are not considering the parachute as buoyancy force. Number 2. Releasing a stone from our hand and it falls down on the ground, as the only force acting on it is the gravitational force. So the released stone is in free fall. Number 3. The moon and the artificial satellites are moving only under the influence of the gravitational field of the earth, so they too are in free fall. For a freely falling object, the velocity of object on reaching the earth and the time taken for it can be calculated by using Newton's equations of motion. So, initial velocity is equal to u is equal to 0. Acceleration is equal to a is equal to g. Note that the value of g is the same for all objects at a given place on the earth. So, if we drop any two objects from the same height, and as they freely fall, they will reach the earth at the same time, irrespective of their masses. For example, when we drop a feather and a heavy stone at the same time from a height, both ideally should reach the ground at the same time. But they don't, because of the buoyant and frictional force due to air. But when the same experiment is done in vacuum, they both reach the ground at the same time. We might have generally heard or seen in photos that astronauts and the objects in the space appear to be floating. The reason behind this is weightlessness. What is weightlessness? Weightlessness is caused by being in the state of free fall. This means that the value of g is not 0 at such a height of the spacecraft, but only 11% less than its value on the surface of the Earth. Though the spacecraft is not falling on the Earth because of its velocity along the orbit, the only force acting on it is the gravitational force of the Earth, and therefore it is in a free fall. We have studied about potential energy in our lower standard. So what is potential energy? The energy stored in an object because of its position or state is called as potential energy. This energy is relative because as the height of the object from the surface of the earth increases, the potential energy also increases. Potential energy at a height h is equal to mgh, where m is the mass of the object. Potential energy on the ground is equal to 0. What is gravitational potential energy? That is GPE. Gravitational potential energy is the energy of an object because of its position in a gravitational field. Therefore, GPE is equal to mgh. This gravitational energy decreases as the height of the object increases. This means if h is equal to infinite distance, then g is equal to 0. Hence, GPE is equal to 0. If h is equal to large distance, then g is less than 0. Hence, GPE is greater than 0, thus is positive. If h is equal to small distance, then g is greater than 0, and hence GPE is less than 0, thus is negative.